Hello, everyone. I'm Mihai Maruseac from Google Open Source Security team, but I will not talk about Google stuff except on this slide and near the end, and that's all. So everything else will be technology that we discuss under Open Source Security Foundation, so OpenSSF. It's open source working group. Anyone can join. You can find OpenSSF calendar, find meetings that are interested in, and join them. Okay, so we're going to talk about AI and security. And first, let's begin with some diagram. I'm going to say AI, I'm going to say ML. We're going to say they are the same, even though they are not exactly the same. Let's say they are the same for this purpose. And I'm also going to refer to traditional software, which is software that doesn't use AI. I'm differentiating between them because I want to talk about stuff that is in common between the two, stuff that is different. And what is in common between the two is they both had a similar history. Both AI and traditional software first started as hobbies. For traditional software, we had people tinkering in their garages, creating software just for their own needs, and so on. Then we started people in academia, people in some companies starting selling for big industry. And finally, it became a commodity. Everyone started having PCs at home, and now you started having programs that people would use by themselves, games, and so on. The same happened with AI. Initially, it was more like research labs, like the first AI spring, the first AI winter, and so on. Then it became commercial. We had apps like Translate. We had apps like get from voice, understand your voice, and perform tasks like Siri, like Alexa, and so on. And now with LLM, it became a commodity. Anyone can develop apps on top of LLM. It's very simple. I'll have another slide later where I'll show some examples. Unfortunately, the bad side also happened in parallel. As the technology became more and more widespread, we also started having more and more attacks, more and more criminals, more and more cyber issues. And let's see some of them. So the one that is on top of almost everyone's mind is prompt injection. It is OWASP's risk number 1 out of 10. It is showing up in almost all security assessment for using AI. And it's very important. However, we also had a similar issue in the 90s with traditional software. That was SQL injection. You had the same issue where you had a web page and that was connecting to SQL behind the scenes, and then people could inject stuff and pop your database and so on. We fixed that problem. And we fixed it by requiring some formalism across the queries. And instead of running directly with what the user passes in, you process that and then you send this to the database. We can do the same for LLMs. We can add a filter between the user and the actual LLM. That would,
If you don't have any agents attached to your system, like what's the harm of prompt injection? Because they can't do anything anyways. All they can see is output.
So you might have output that is private to the company that you wouldn't want to expose. So there is, for example, there is a puzzle game online, Gandalf, where Gandalf is an LLM that has a password. And you have to chat with the LLM to discover the password. It has, I think, like 10 levels now. Each level is more complicated, has more filters in front of you, and you have to guess the password at the end. And if there is no agent there, it's just one single string that you have to retrieve via prompt injection. Okay, so moving on, another thing that is important is data leakage, where users' data is leaking out via agents, either via prompt injection or by the fact that the AI confuses between one Jeff and another Jeff, and it's giving you details for the second Jeff where you're actually asking details for the first one, you're the first one. So that is a problem. And we also had the same issue in traditional software, like data leakage, datasets breaches, and GDPR breaches, and so on. Another issue is getting malware. We have malware in models, and we also have models that have been maliciously trained. So the first link here is actually to a research paper that ingests malware, whereas the second one is actually a model trained on 4chan. And Malware becomes important because both most ML frameworks, they are very powerful and they have operations that can run arbitrary code. So here I give example of TensorFlow and PyTorch. In TensorFlow, there is this Lambda layer that can run arbitrary code, and you can ingest it into the model. So it's easy to change the model architecture to run arbitrary code while it's performing inference. And on PyTorch, the PyTorch models are a pickle, and pickle unloading is unsafe because it basically needs to deserialize the object into the Python stack, and that can run arbitrary code. So it's very easy for somebody that has access to the model bits to modify the model and run arbitrary code while you're trying to run an application. And this is the issue why Hidden Layer created, I think it's Hidden Layer. Yeah, they created a specific format called safe tensors, which is supposed to hold just the weights of the model and no pickle anymore. So the weights would be like in a JSON format. And this way, your model will be safe when you load your model. It will not be able to execute arbitrary code. However, the job that was converting from a PyTorch model to the safe tensor model was running across all of the models that got submitted to the job. So it was very easy for an attacker to send a model that was using pickle, was running arbitrary code to install some persistence into the job environment itself, and use that to modify all of the next models that get converted and modify the models to insert malware into them, even though the model was just a list of weights. And this is very similar to an attack that we have seen around 4 years ago, SolarWinds, where the build system itself for some artifacts was compromised, and any artifact that got built there was compromised in the end. Okay, so why is this important? We have seen AI used for coding. So GitHub Copilot, almost everyone uses it, or now I forgot, there are new ones that everyone wants to use. We also have applications that are building full applications by chatting with GPT. You are saying, I want you to build me this game, and it has these features, and this is what I want you to do. And the GPT is giving you some wireframe, and then you keep asking until you get the full application. We also have agents and LLMs being used for smart homes, and this will become more and more prevalent into the future. We also have LLMs being used for security. So this is an example where LLMs are being used to extend fuzzing to discover security vulnerabilities. You discover a piece of code that is not fuzzed enough, and you ask an LLM to write a code that would exercise that piece of code. The LLM would generate some code for you. You try to compile it. If it fails, you ask another LLM to fix the compilation issue. If it passes, you get some results on the fuzzing. You can ask the LLM, okay, but this increases the fuzzing coverage by just this small percentage. Can you increase it more? And you keep chatting with the LLM, and it will help you discover vulnerabilities and attack other systems later. And finally, LLMs are also used to solve package dependencies in high-performance computing. So imagine a supercluster that is used for, let's say, astronomical computations. They also need to install dependencies from PyPI. They have a lot of requirements. They are already using AI and LLMs to determine what set of dependencies can be installed, what set of dependencies should be upgraded, and so on. So if that LLM is malicious and installs a malicious version of another dependency, that can result in further poisoning all the computations. Okay, so what we can do is, let's look at the supply chain in how we are building a model. I'm going to focus now on just securing the model, but in general, we should think about securing the entire application around the model, not just the model itself. Some of the attacks around ML systems are hard or almost impossible to fix if you focus just on the model. Instead, you should think about the way you integrate the model into the entire application. So for example, the scenario that I started with using prompt injection, it's very hard to make the model resistant to prompt injection, but it's much easier to have filters in the application that would look at the user query and try to detect if the user tries to bypass your query, tries to bypass your protections, and also at the output to see if your model is outputting stuff that it shouldn't. So it's easier to prevent some of the stuff at the application level instead of the model. But for now, let's just focus on the model. So in general, when you want to train a big model, you don't have a single person training the model from scratch. You have actually, let's say, 4 different categories. You first have people that work on data. They collect the data, they clean the data, they run a lot of processes to make sure that the data that you want to use is up to the task. And it's an iterative process, it has multiple loops and so on. Then you have the, let's say, infrastructure people. They are the people that actually control the training. They do the training job, they have the training framework, they optimize for storage, they optimize for performance, they do all of this stuff. And here you have dependencies for the models. It could be, for example, if I'm fine-tuning a model, I can have another model as a dependency. I have the ML framework as a dependency. So if I use TensorFlow, that's a dependency that it should be considered for security. Okay, after the training, then there is the storage folks. They have to make sure that the model is available for applications or for further training. They have to make sure that the model, while it is in storage, cannot be tampered with, that the model there is easy to use, it's accessible, especially like if you have a big organization and you keep moving your model from one place to another, you would still need to respond to, for example, legal queries like what was this model trained on, what data set, and so on. This is under the storage folks. And then the 4th layer in the blue is the application. They are the ones that build around the model. They only care to be sure that they picked the right model for the application. And even then they can be fooled. You can say like, this model is a model that is useful for your application, it performs well, but actually all those metrics could be faked. So let's look at the first example for protecting the models. This time, we just want to make sure that the model that gets used to the application after being in storage is the same model as the one that got trained. So even if an attacker gets control over the storage and tries to modify the model bits, they won't be able to do that. We'll be able to detect the tampering. Basically, in traditional software, we solved this via signing the artifacts. And that's what we're going to do here for models. We are going to sign the models, and we are going to verify the model signature while it's in storage, for example, in TFAB or, in Hugging Face, or we are going to verify the model signature before we use it in the application. So this is kind of how we imagine the workload to be. So we start with the model trainer here in the middle. The mouse can see, okay. And as the model gets trained, the workload that trains the model would contact a certificate authority from Sixt. Sixt is very similar to Let's Encrypt. What Let's Encrypt is for certificates, Sixt is for digital artifacts. So you contact a certificate authority, and that gives you back a certificate that is valid for a few minutes. You can use this certificate to sign one artifact, and after that, you no longer care about the certificate. You can discard it. Contrast this with signing with PKI, with private key infrastructure, where you have to maintain your key. You have to know when your key got stolen and discard it, and notify all of the people saying that anything that got signed with this artifact, with this key, is no longer valid because some attacker got access to my key and now can sign malware with that. Okay, so now the Sixt CA gives a certificate. As soon as your job finishes, the job would use that certificate to sign the model, and this signature would be stored into a transparency log. This transparency log could be used to identify all of the models that got trained by a specific identity, let's say a specific company, specific user, and so on. So it's very useful for transparency. And you get back the log inclusion proof. Since it's an append-only log, you basically get some proof to make sure that you can also verify offline. You don't always need to connect to the transparency log. And then you upload the model to the model hub, and you also upload the signature and the proof, the inclusion proof. Now, as a user, you download the model from Model Hub, and you verify it, and then you use it. And why is signing models hard? First, the main component is that the model size is huge. Compared to traditional software, which rarely gets above several hundred megabytes, models are gigabytes to terabytes. So hashing will take a lot of time, and we need ways to optimize this. In general, when you hash something, you wait for that thing to be on disk, and only then you read it from the disk, and then you hash it. We don't want to do this for models because we save a large amount of space on disk, and then we have to read it again. So ideally, we would merge hashing during the training process, so it will be like an iterative process. We also need to take into account that models are not built in just a single host. Instead, they are trained on a distributed environment, and every host in the distributed environment can write only some bits of the model. So ideally, we would also do the hashing in a distributed fashion and collect all of the hashes together. Another issue that makes model signing harder than traditional software is that we have two different concepts for models. One is the model itself that contains the weights and the model architecture such that you can deploy it in another application without having to copy with you the code that was used to train the model. The checkpoint, the other format, is just the weights. In general, is used for restarting the training, or in case something happens with it, or in case your application and your training job use the same architecture and you don't envision changing architectures, you can just keep the weights and you don't have to also serialize the architecture. But because we have different formats, each time you convert from one to the other, you have to rehash the model because it's not just add another set of files to the weights. It's a totally different architecture. And the other issue is that during training itself, you generate only a specific number of checkpoints. You don't generate all of them. You don't save all of them. You only keep the last, let's say the last 10 or the last 10. But ideally, you would sign all of them because imagine an attacker. They could connect to your training job. They could see that you just wrote a checkpoint to disk, that your training job just wrote a checkpoint to disk, maliciously modify the checkpoint, and then cause your training job to crash. When you start your training job again, you are going to start from a checkpoint that has been tampered with, and now everything that you built from that point on will be altered. So we need to sign all of the checkpoints during training, but because hashing is expensive, you don't want to do it very slowly, so we need some performance there. And then some models also see changes after the training happens. So both on Hugging Face and on Kaggle, in general, you have a model under a single name, so let's say Llama, but inside that directory, you have model files for multiple directories. You have files for PyTorch, files for TensorFlow, and so on. So basically what happens is somebody trains a model in one framework and uploads that to TFHub or to Kaggle, to Hugging Face, and then they convert that model from one format to another and upload those files to the same model hub. And you want to make sure that the hashing is across everything that is in that directory, so the entire model, the entire set of weights in all the formats. But as the user, you only care about the model that you are using for your frameworks. So for example, if I'm using PyTorch to use this model, I only care about the PyTorch files. I don't care about the TensorFlow files. I don't care about CoreML files and so on. So on signing, I need to hash the entirety of the model in all possible formats. But on verification, I only care about a specific subset of the files. And then we also have the issue that inference is done in a distributed fashion. So every host would like to only verify the parts of the model that it touches instead of having the controller verify the full model and only then start doing the inference, because then the time to the first token would be very long. So we have this API for this library for signing models. It's designed into 3 layers, and then we'll build a public API on top. But rather than discussing this, let's do a demo. So I'll go to this notebook. I hope everyone can see it. So instead of training a model inside the notebook, I just download one from Hugging Face. So imagine that this step here is actually training the model. And I actually have a 3 gigabytes model. So if I run this cell, that should be 3 gigabytes. And now I can actually start signing it. So this is part that would be integrated into the model hub, into the model training pipeline. But now, because I downloaded the model instead of training it directly, I'm doing it separately. Okay, so let me run this. Okay, so the first layer in the architecture is defining how do I hash a component of the model. And in this case here, I'm splitting the model by every file, and I am hashing every file with SHA-256. So I have two options to choose here. I can hash by tensors, and what hashing algorithm I can use, SHA-256, SHA-512, Blake2, and so on. So here is file and SHA-256. And then the next layer is the one that takes the model and computes the hash for it. So this is the part that will take the largest amount of time, because this actually needs to look over all of the bytes in the model. It should be around 16 to 24 seconds. So by the time I finish talking, it should be done. This is the part that will build us our model. And come on. I have here a parameter to allow symlinks, which for some models that have symlinks to different parts in your hierarchy, so you want to share some information, you want to share some architecture between different models, you would want the signing to be able to see the architecture. And you would only have the weights in the model directory, so you don't duplicate a lot of the information. Okay, this one finished. So the next layer is the layer that performs the signature. So this is the layer that would connect to the Sixt certificate authority to receive a token. So because I'm a human doing this instead of a job, I actually have to run a separate step where I am connecting here, and I'm signing with my identity, and I get back this thing. Okay, now let me see, how do I do this? Yeah, I have to paste it. And I have to paste it here. Okay, and at this moment I have a model signature. And we can inspect the signature itself. So the signature is a JSON file that I can display, I can look at. So it says it's a Sixt bundle, that is the format for the signature. It contains a certificate, the certificate that is valid for only 10 minutes. And then it contains an inclusion proof. So you would know that this has been signed at this point in time across the entire transparency log, and you can verify this without connecting to the Sixt store. You can just look at the transparency log itself. And then it contains the envelope, which is the part that gets signed. And here we have the signature itself, and we have the payload, which is basically, the payload, the one above. This one, this is exactly what I hashed. And we can inspect that too. So I extract it out, and then I look at it. And it's a big JSON. And in it, we can see that I have one file for the Rust version of the model with its own hash. I have a TensorFlow file for the model. I have a tokenizer, so this is a language model, so I have the tokenizer in it. So every file that uses the model will have to verify the integrity of this file. And let's see, what do I have in here? Let's go up. You can see I also have the model for the ONNX format. I have the model in CoreML format. So there are a lot of formats in here. As the user, when I want to verify, I don't need to check the integrity of everything. I only check the hashes for the files that are relevant to my architecture. And actually, let's do some verification. Because again, I'm doing it manually. I'm going to run some cells. So the first one is verifying just the envelope of the signature. So I have to pass in here my email and the identity provider. And this will basically be, if you have a model that should come from Google, you would pass a Google credentials in here to verify that the model has been from Google. So now if an attacker tries to tell you, oh, this is a model trained by Google, but the envelope verification fails, you would know for sure that that model has been tampered with. So this part would be fast because this is just checking the envelope. And now the next part, which is serializing the model that I have on disk and comparing it against the source of truth contained in the signature. This will also take a little bit amount of time because I need to serialize the model again. So the hash that comes from the signature is considered to be the source of truth. And what I'm hashing now is to make sure that what I have on disk matches that. And I should get the signature is valid. And now let me put on the attacker hat on, and let's say I destroy the model. I inject I inject some malware into the model. In this case, I just delete a file, but you can imagine that at this step, I do some malware. If I try to verify the model now, the envelope would still pass because I still say it's a model produced by me. But when I try to serialize and check again, this time it will fail. And in a little bit more time, we'll see that it should fail. So what we can do, we can also compare, the signature is invalid. So now you can detect that somebody tampered with the model. Okay, so in the optional explorations here, first I compute how long it will take to hash the model using traditional hashing, like the dir hash scheme. So I hash every file into the directory, I sort that, and I hash the output. This is going to take a little bit longer. So here, when we are hashing the model with the library, it took around 10 seconds, 13 seconds. Whereas this part where I'm hashing with traditional approaches should take around 26 seconds, something like that. And 24, close enough. Okay, so the other option is to show you other layers in the model. So for example, here, instead of hashing by file, I split every file into the model into shards of 1 million bytes. And I hash the model by shards. And instead of using SHA-256, I will hash with Blake. So this one is fast. This one is the serialization with this new approach, and should also finish in a few seconds. And then the next part, signing it to Sixt and verifying it would happen the same. Just for the interest of time, I'm going to skip the rest of the steps. Okay, so what we have to do next is we want to integrate this with model frameworks such that you train your model, and then when you say model.save to save the model to disk, it will sign for you, it will connect to Sixt, get the signature, do everything for you directly. We also want to integrate with the model hubs. You could go on, let's say, Hugging Face. You would select your model that you want to use, and in the model card, you will see a badge, like you see the badges on GitHub, that will say this model has been signed, and you can click on that, and it will show you who signed the model and so on. Think the similar way as you saw a padlock in the URL when you use Chrome for HTTPS sites. You click on the padlock, it tells you this site is secure. You don't have the padlock, something is fishy. We also want to do more performance improvements for hashing to be even faster. We want to support incremental updates. So I already signed the model, but now I add more formats. I don't want to have to rehash everything. I only want to hash what gets added and compute a signature over the entire thing. And then we want to make sure that we can use this model hashing scheme for other information in the supply chain. Okay, so now let's move on to protecting the supply chain across the entire space. So from the data set all the way to the application. This is more experimental at the moment, but we can still do it. I'm not going to run a demo, I'm just going to show screenshots for this one. So right now, we can train a model on GitHub Actions and generate a provenance for that model that will list us how the model got created. So in this repository, Sixt model transparency, you can go select Salsa for ML example and then trigger the workflow and select a model. And it will train a model with that framework. And at the end of the job, I guess I skipped that part. Let me show you that part separately then. So at the end of the job, let's pick one that finished. I will have both the model. I will have the model that got trained during the GitHub action, and I'll have this JSON file that represents the provenance. So I can inspect the provenance when I get a model. When I download the model from the model hub, I can also download the provenance, and I can inspect them manually. Or I can build automation. Since this is JSON, it can be also parsed by machines and by humans. I can build automation that would verify on this pipeline for this application, I only trust the models that are being built by this organization, or only open source models and so on. So you can do all of that. And let's look at what the provenance looks like. 1 second. Let me get to the slides. Slides. Okay. No. Okay, this is the slide. So looking at the provenance, it's a JSON document again, and we can see that it is signed. So once it's generated, you cannot tamper with it, you cannot lie about the source of the model. And it has this payload field. So that's where we have the data about the model. And we can look into the payload. It will tell us, this is the model that we have built. This is the hash of the model. This is the part that we want to make sure it's the same as the signing part. And looking more into the payload, we can see it has been built by a separate GitHub repository. So that's where the security part lies in. An attacker would have to compromise 2 separate repositories in order to lie about the source of the model. So that's a little bit harder. And it will also say at what point into the repository I have built the model. So now I can just go to that repository, that commit, and look at the source code, investigate everything, and see if it exactly matches what I was expecting. We actually want to do more for this. We want to include more information. So we want to include all the data sets, all the training frameworks, everything directly into the provenance. So you don't have to go into the repository and search for that. We also want to expand beyond the GitHub Actions. So instead of training a model in GitHub Actions to get the provenance, we actually want to create certified model trainers, certified secure trainers that will generate the model in a secure way that will give you the provenance. You can analyze all of this. And while we do this, we should also make sure that Jupyter or Colab give you an option. You could run the cell in any order you want. And at the end, you get the model, you get the provenance that also tells you exactly the order in which you run the cells. So you can no longer lie, oh, I ran cell 1, then cell 5, then cell 2, 3, 4. It will be included in the provenance, and it will show exactly the way you generated it. And this basically brings another document to the ML metadata side. So we already have AI bill of materials. We have model cards, and now we're also bringing Salsa. Each one of them focuses on something different. Each one of them is complementary to each other. Probably at some point in the end, we'll collapse everything into just one, but we need people from the community. We need input from everyone. Okay, and this is basically the diagram that we have seen already. Looking at traditional software in general, you have one binary that has a lot of dependencies, and those have also a lot of dependencies, but at the end, the tree is shallow, so it's very wide, but shallow. Whereas for ML, for large language models, in general, you have a model that you use in your application that got fine-tuned from one model and some small set of examples. That model itself got fine-tuned from another set and so on. So in this case for ML, the tree is thin but deep. We can still understand all of this tree. There is this project that people have been working on for traditional software called GUAC, which is Graph for Understanding Artifact Composition. It's initially started with Neo4j, but now it's any graph database can be used for this. You basically take all of your dependency chain, put them into a graph, and can ask queries on it, can run arbitrary queries, and so on. So we want to do this for ML too. Okay, one more thing. Let me put on the attacker hat again. And let's say I want to attack some users using ML. I can train some malicious models. Let's say I have 2 models. One is an evil model. The other one is the model on GPT-4chan. So the first one has malware. Users are not going to just get the model from me. So I need to upload the model to the model hub. And of course, I need to give the model some nice names into the model card. So I would say the first one is a malware detection model, and the second one is a friendly chatbot. Some of the users might download it. They only read the model card. Users that look at the model name might say, yeah, this doesn't seem right because one of them says evil model, the other one is GPT-4chan. But there is nothing stopping me from renaming the model. So I will call the first one nice model and the second one GPT-4 friend, and that's all. So this is why we want to do provenance for models, because now you can no longer lie. The provenance itself will tell you this model has been built exactly from these sources for this specific purpose. We have a white paper that we wrote near the beginning of the year that lists the vision of this. We are kind of going beyond that now, and we have more information, so there will be more information released later. But the general idea is that we see that AI is getting used more and more, but also we see that attacks happened more and more, so at an accelerated pace. And we still think that protections to AI could be very similar to protections from traditional software. We just need to adapt them in the cases where AI is different. And I will end with some QR codes. The first one is the repository that has the model signing code and the Salsa Pro demo. The middle one is the white paper, and the third one is the OpenSSF working group. If you are interested, you're more than welcome to join. We can discuss anything that is AI and security in there.
Thank you. So we have time for questions. If you have a question, please raise your hand and we'll bring the mic to you.
Great talk, very interesting concept. So when you were validating the signature, you were using this pathlib.path. But it seemed to me you're just using the model's name. You're just referencing the model. Is it the path to where the model is, or is it just mentioning the model's name?
It's the path to the model. So this is going to be a demo that I didn't do before. But if I go back to the collab, 1 second. So if I go back to the collab, I can actually try to rename the model. Files. And let's say I would rename this. Model. So now the model that I downloaded is in this directory. So I downloaded the model somewhere else. If I want to verify the signature, I will also have to use the same path. So here, when I do the verification here, this one will have to be model, because that's where I downloaded the model locally. And it should still fail because I changed the hashing scheme when I run the demo later for the next of the iterations. Plus, I also deleted this file. So I should still have a signature invalid, but if I wouldn't have deleted that file, it would have passed.
Other questions?
So you mentioned about AI bomb, which is very interesting. So I'm guessing it's built on S-bomb?
Yes.
Do you have a specification of this already, or no?
No, there are, I think, 4 different working groups that work on that. And we need to see a standard. And then we need to have generators for this that are working for open source and for companies. And we can go from there. But right now, this is very greenfield at the moment.
Are you aware of C-bomb?
S-bomb? Oh,
No,
C-bomb. C-bomb, no.
So cryptographic bomb.
Okay.
Yeah, that's a standard already in Cyclone DX. So I'd recommend you to look at that.
Okay, yeah, thanks.
Any more questions? Well, if not, let's thank Mihai.